A mechanism is the sequence of elementary steps by which a reaction proceeds. So if we look at this reaction, here we have nitrogen dioxide plus carbon monoxide, giving us nitric oxide and carbon dioxide. Our two reactants don't go to our products in one step. There's a sequence of elementary steps by which the reaction proceeds. There's a mechanism for this reaction. And one possible mechanism for this reaction shows the mechanism in two elementary steps. In the first step, step 1, we can see it's NO2 plus NO2, giving us NO plus NO3. And then in the second elementary step, the NO3 that we just made, right, NO3 plus CO, gives us NO2 plus CO2. And any possible mechanism must have elementary steps that add up to give the overall reaction. So if we add these two steps together, we should get the overall reaction. So let's put all of our reactants on one side. So we have all of our reactants over here. So that would be NO2 plus NO2 plus NO3 plus CO. And then we'll put all of our products on one side, so all of this stuff. So we have NO plus NO3 plus NO2 plus CO2. Now we look on both sides, on our reactants and our products, and let's see what we can cross out. Well, we have an NO2 on the left, and we have an NO2 on the right, so we can cross that out. We also have an NO3 on the left and an NO3 on the right, so we cross those out. And we see what we are left with. We're left with NO2 plus CO, so we're left with nitrogen dioxide plus carbon monoxide. And then for our products, we have nitric oxide, NO, and then we also have carbon dioxide, CO2. So we added our two elementary steps of our mechanism together. We added step 1 and step 2 together, and we got this for our overall equation, right? Which is the same one that we talked about up here. So this is a possible mechanism for this reaction. Also, note the presence of NO3. So here we have this NO3, which we made in our first elementary step. And then we can see in the second step, the NO3 is consumed. So we call this NO3 an intermediate. So this is an intermediate. It's made in one step of our mechanism and consumed in another step. So the intermediate is not a reactant, it's not a product. It's something that we can detect sometimes, and this helps us figure out mechanisms. So if you're able to detect a certain intermediate, that helps you figure out possible mechanisms for reactions. A possible mechanism must also be consistent with the experimental rate law for the overall reaction. Our overall reaction is 1 NO2 plus 1 CO gives us 1 NO plus 1 CO2. And the experimental rate law for this overall reaction is the rate of the reaction is equal to the rate constant K times the concentration of NO2 to the second power. So our reaction is second order in nitrogen dioxide. And if we look at our balanced equation here, here's nitrogen dioxide. Notice it has a coefficient of 1 in our balanced equation. So we can't just take the coefficient of 1 and turn that into the exponent, because experimentally we've determined the exponent to be a 2 and not a 1. So you can only take the coefficient and turn it into an exponent if you're talking about an elementary reaction. Also note that this reaction is 0 order in carbon monoxide, right? So this, you don't see carbon monoxide appearing in your rate law. Let's look at the mechanism and see if we can understand or explain the experimental rate law. So the mechanism, in step 1 of the mechanism, we formed our intermediate, which was NO3. And it turns out this is the slow step of the mechanism. In the second step of the mechanism, we took our intermediate NO3 and we formed another product over here. This is the fast step of the mechanism. And the slow step of the mechanism is called the rate determining step. So step 1 here of our mechanism is the rate determining step. And the reason why this is the rate determining step, let's make up some times here so we can understand this a little bit better. Let's say that this first step, the formation of our intermediate, takes 1 second. So it takes 1 second to form our intermediate. And then the second step of the mechanism is fast compared to the first. So it should take a much smaller amount of time, and I'm just going to again make up a number. Let's say it takes 1 times 10 to the negative 8 seconds for the second step of our mechanism to occur. So what's the total time for our reaction? Well, we would just add those two times together, 1 second plus 1 times 10 to the negative 8 seconds. So we'd get approximately 1 second for the total time of our reaction. So the effective rate of the reaction is determined by the time consumed during the slow step. Right? The slow step took 1 second, and that's pretty much how long our overall reaction took. So we can say that if we're trying to find the rate of our overall reaction, right, trying to find the rate of the overall reaction, that should be equal to the rate of the rate determining step, as we've just seen by this example over here. So if we can figure out the rate law for the rate determining step, that's a good approximation of the overall rate of our reaction. So we can figure out the rate of the rate determining step because this is an elementary reaction. Step 1 is our rate determining step, and this is an elementary reaction. And we talked about in an earlier video how to find the rate law for an elementary reaction. Right, you would start by writing the rate of the reaction is equal to the rate constant. For step 1, the rate constant is K sub 1, so the rate constant is K sub 1, times the concentration of our reactant. Let's see, we have NO2, so we put NO2 in brackets. And since the coefficient here is a 1, remember for an elementary reaction, you can take the coefficient and turn that into an exponent. So this would be to the first power. And then we have another NO2 over here, so we multiply that by the concentration of NO2. And once again, our coefficient is a 1, so since this is an elementary reaction, we take our coefficient and we turn that into an exponent. So now we have our rate law for our rate determining step, and we could even go further. We could say that the rate of our rate determining step is equal to the rate constant K1 times the concentration of NO2, and this would be squared. Right? So concentration of NO2 to the first power times concentration of NO2 to the first power is concentration of NO2 squared. And so we see that this has the same form, right? This rate law that we just wrote has the same form as the experimental rate law. And so our mechanism is consistent with the experimental rate law for the overall reaction. So our overall reaction is second order in nitrogen dioxide and 0 order in carbon monoxide. Notice that carbon monoxide doesn't appear until the second step, right? So here's where carbon monoxide appears, and that's not the rate determining step. And so that's one way to think about why our reaction is 0 order in carbon monoxide. Also notice that this K1 here for the rate determining step, K sub 1, should be equal to K, the rate constant for our overall reaction.